Okay, so today we're gonna talk about simplicial sets and semi-simplicial sets and simplicial spaces, and hopefully relate this back to uh, configuration space, configuration spaces in the interval. Yeah. Okay. So yeah. So remember, like an Eilenberg-MacLane space is a space who has only one homotopy group concentrated in degree n. And so last time we gave configuration space models for KG1s in terms of configurations of points in the interval with labels in G that vanish near the boundary. And in particular, we did this for G non-abelian, which required that we were in dimension 1. Because in higher dimensions, if points collide, you don't know in what order to add their labels. Okay. So yeah, the theorem was that for all n greater than 0, or n groups G, which abelian if n is at least 2, there's a space KGN, the Eilenberg-MacLane space, whose homotopy groups are concentrated in degree n and are exactly G. And we gave this configuration space model for them involving it's just points in the interval labeled by G. Sorry, yeah, points in the interval labeled by G that vanish if they enter the boundary of the interval, and when the points collide, you add their labels. And this makes sense when G is a topological group, but if G is discrete, then this is a model for Eilenberg-MacLane spaces. And sort of the point today is that this is actually the realization of a simplicial set. And so, the traditional way of introducing this space is with simplicial techniques, and then sort of, I think the number of people who know the simplicial set formula for this space is 10 times the number of people who think of it as a configuration space. So maybe the point of this lecture is just if you meet someone on the street and are telling them about models for KG1, you won't seem weird. Okay. Yeah. So, any questions before we begin? Or before we move on to simplicial things? So, so I'm going to start with semi-simplicial sets because I think they're easier to. They're in my opinion, they're more intuitive. Simplicial sets are slightly better behaved, but I think they're less intuitive. Okay, so delta ing is going to be the category of finite non-empty sets in order preserving, with morphisms being order preserving injections. So up to isomorphism, every object in this category is just a set, every object is isomorphic to this ordered set, which will denote brackets P, which are just the numbers 0 through P with a standard order. And it won't really be that important to differentiate between this category and the skeleton, where these are the only objects. Okay. So and we have morphisms. So the basic morphisms are these delta i's. So you can map this set 0 through P minus 1 to the set 0 through P. The only injections are I guess let delta I be the injection that misses I. These are all of the injections. So POM in this category from P minus 1 to P is just the set delta 0 through delta P. And so in general, the Hom set from Q to P are just compositions of these basic injections. Yeah, and I guess this Hom set will be it'll be empty if Q is bigger than P, and it'll be a single element if Q equals P, because there's a unique order preserving these injections are required to be order preserving, and there's a unique order preserving injection from an ordered set to itself, or finite ordered set to itself. So when Q equals P, it's the composition of zero things, and then And any questions about this category, other than like what it has to do with anything we were talking about? Okay, so a semi-simplicial set is a I guess I forgot to write contravariant, is a contravariant functor from this category to sets. So from the so given any non-empty ordered set, the output is a set. And so given one of these functors, we can evaluate it on our standard sets of size p plus 1, and we're going to name that xp. So given a semi-simplicial set, we get for every non-negative integer p, we get this set xp. And functoriality tells us that we have morphisms from p minus 1 to p, and functoriality gives us a map of sets from xp to xp minus 1. So we get two maps from x1 to x0 corresponding to the two order preserving injections from 0 into 1. And then there would be three maps from x2 into x1. So, what we're going to think, maybe I should have said this, we're going to think of these xp's as the set of p simplices of our space. Yeah, so now the next topic is how do we get from a simplicial complex to a semi-simplicial set? So we'll let Y be a simplicial complex, and we'll let YP be the set of p simplices. I guess this is a typo of Y. I don't know why yellow is the default color. So we'll view YP as a subset of the power set on Y0. Sorry for the typo. Yeah, so because in a simplicial complex, every simplex is determined uniquely by its vertices. So we can view the set of p simplices as just a p simplex. The data of a p simplex is just the data of p plus 1 vertices, and we're gonna pick an order on the vertices. It doesn't matter, just pick a total order on the set Y0. And then I claim, once we've picked a total order on the vertices, we can build a semi-simplicial set. So what do we need to do? Given, so out of the simplicial complex Y, we're going to build a semi-simplicial set Y bullet that will sort of record all the information of Y. And so what do we, this is a functor, so you give me an ordered set O. Let's say it's size p plus 1. The value of the functor on that set is going to be the set of ordered preserving maps from O into Y0, such that f of O is a p simplex. And so that tells you what to do on objects, and on morphisms you just precompose. Okay, so probably this is slightly too abstract, but the next page will be a concrete example. But so what happens when you plug in if we just think O is, you think O is just P plus 1, is up to isomorphism, it's just P plus 1. Or sorry, it's just P. It's confusing because the thing called P is a set of size P plus 1. But they're sort of, the only way to change that is if you want to say a 0 simplex. Or if you want to say a 1 simplex is 0 dimensional. Like if a point is a 1 simplex. So yeah, sorry for okay. So yeah, so let's say O is just this standard set 0 through P. Then what's the data of a order preserving map from O into the set of vertices? Well, if you have an order preserving map, an order preserving injection is uniquely determined by its image, right? Normally functions aren't determined by their image, but that's, but when you pick an order on the domain and the range, and insist that the function's injective, then the function is uniquely determined by its image. So the data is just the image. So this is just a set of P plus 1 vertices that forms a simplex. So this set is always non-canonically isomorphic to YP, and then if you pick an isomorphism, I guess it's canonically isomorphic. Yeah, sorry. So this is maybe sort of overly functorial language for just saying that this functor is going to send P to the set of P simplices of our simplicial complex. Yeah, so I've maybe written it out this way so it's clear why it's a functor, but concretely, this functor just sends the standard set of size P to the P simplices of the simplicial complex. Any questions before we sort of illustrate this in a concrete example? Okay, yeah, so let's say Y is the simplicial complex. So the white triangle isn't there, but the purple triangle is. So the Y0 is just A, B, C, D, E. Y1, instead of using like nested sets, I'm going to denote simplices with this square bracket. So Y1 is just a set of one simplices. So like AD is in Y1, but AC is not in Y1 because there's no edge there. And then Y2 is just the simplex BDE. And then you have these maps D, which are called face maps. The effect is they just send a simplex to its face. So look, D1 of BDE is B1 means forget the first term. So B is the 0th term, D is the first term, E is the second term. So D1 of this is BDE, D0 would be DE, D2 would be BD. Yeah. Similarly, like D0 of AD is A, D1 of AD is D. Yeah, so if you have a simplicial complex, you get this semi-simplicial set that records all of the information of your simplicial complex. Any questions? Hopefully this slide makes more sense than the previous one. Okay. So given a
Jeremy, can I make a comment?
Oh yeah.
I mean, there's a slightly annoying thing about this, which is that you have to choose an ordering, right?
Yeah.
So it doesn't quite define.
You don't know what, if you have a 15 simplex, you don't know what the 8th base is.
Right. So it does not define a functor from
Yeah.
simplicial complexes to semi-simplicial sets.
Yeah. And also, which
But there are ways of dealing with this little issue.
yeah. Or I mean, if you don't care about functoriality, then
Yeah. Okay. Yeah.
uh,
Exactly.
yeah, this is another way of.
Yeah.
But yeah, there's another point that which I'll raise later is that. Oh, actually, I'll just say it later. But there's another in some ways. Well, I guess depending on how much you care about functoriality, more important difference between simplicial complexes and semi-simplicial sets.
Okay. And something else I was going to say just very quickly is that there's a different way of associating a simplicial set to a simplicial complex that I like, which is given a simplicial complex, you can construct a category in which the objects are the simplices,
Yeah, but you're going to
and
very
then you put
specifically
an
subdivide,
arrow.
right?
Yeah, you put an arrow if one is a face of the other. And then once you have a category, you can take a simplicial set associated to that category, which is called the nerve, right?
Yeah.
And this is tutorial, and this corresponds to subdividing, and it's nice. Yeah.
Yeah.
Anyway, that was my comment.
Yeah. Yeah. So there's a functorial way of given a simplicial complex, building a semi-simplicial set whose geometric realization is going to be the barycentric subdivision. Yeah, okay. I guess I should tell you what geometric realization is. So if you let di be the map, so remember like delta p is the standard like p simplex. I should have copied it here. I'm using coordinates. I'm thinking of the p simplex as let's go back. What is my model? This is my model of the p simplex. It's one of the two standard models. So it's just points 0 through p that are, each one is in the interval and they're in order. So 0 is less than or equal to t1 is less than or equal to t2, etc. Tp is less than or equal to 1. So this is the standard p simplex. And there are maps where you just include the p simplex as a I face of the p plus first simplex. So concretely, we're just is this formula right? This must be right. Something else you can do. Maybe I'm thinking of the other model, why this looks weird. Or if the formula is wrong, tell me. But where you just double the ti term. Yeah. Does that give enough maps? Do we need to like have t0 be add 0 and tp be add 1 on the right? Maybe. Yeah, so there are standard maps like include the p simplex into the p plus first simplex. Oh, sorry, include the p simplex as a face of the p plus 1 simplex. And so for a semi-simplicial set, we define the geometric realization to be, well, we want each element of xp to be a p simplex. So we take xp cross delta cross the p simplex. So for each element of xp, we have a p simplex. And then these maps d lower I let us identify the boundary of the p simplex with the image. So if y is a simplicial complex and then y bullet is the associated simplicial set, then the geometric realization just outputs y exactly. Any questions? Yeah, so as Manuel said, this isn't functorial because we need to pick an order on y. And he describes something that is functorial, but will output something that's isomorphic to the barycentric subdivision. Oh yeah, so the main warning is that if X bullet is a semisimplicial set, the geometric realization might not be a simplicial complex. It'll still be a topological space, it'll still be a CW complex, but it won't necessarily be a simplicial complex. So, if you take X0 to be a single point and X1 to be a single point, and the higher ones to be the empty set, what do you get? You got a point, you get a one cell, and then you're gluing, you're gluing this point here, and you're gluing this point also here. So you get a circle, and you get a circle with a cell structure that has one vertex and one cell, and that's a perfectly fine CW complex, but it's not a simplicial complex because in a property of simplicial complexes is maps from simplices in are injective. Like you don't collapse any part of the boundary. If any of you looked at Hatcher, this is what Hatcher calls a delta complex. So it's it's a certain it's more restrictive than being a CW complex, but it's less restrictive than being a simplicial complex. Any questions? Okay. So maybe Manuel has other things to hate about semi-simplicial sets, but from my perspective, the worst property is they don't behave well with products. I don't know. Manuel, feel free to add other negative properties. So, for example, let's take X to be this simplicial set I described before. Sorry, semi-simplicial set. So X0 is a point, X1 is a point, and all the higher ones are 0. I don't need to tell you what the maps are because there's a unique map into points and out of empty sets. The map is B goes to A, or D0 of B is A, D1 of B is A. Yeah, so what's the geometric realization of the product? Oh yeah, so one thing to say is, yeah, if you have two semi-simplicial sets, you can just take their level-wise product and you get a semi-simplicial set. Where DI is just going to be the product of the two DI maps. So, we know that X bullet realizes to a circle. So you might hope that X bullet cross X bullet realizes to a torus, to a circle cross a circle. But what does it actually realize to? What is X bullet cross X bullet? Yeah, so you just do everything level wise. So X, the set of 0 simplices of this is just the set of 0 simplices of X squared. Yeah, so what are the 0 simplices of this semi-simplicial set? Yeah, so Michael said, yeah, it's just, in particular, it's just a point. Yeah, so, write this, yeah, so X, yeah, so we just have the set AA and the set BB. And then we have empty sets in all higher degrees. Yeah, so if you take the product, we have 1 0 simplex, 1 1 simplex, no higher degree simplices, so the geometric realization is just going to be a circle again. This is isomorphic. X bullet cross X bullet is isomorphic to X bullet. The realization is a circle. There are no two simplices, so it's not going to be a torus. Any questions about this example? Great. So, you know, answer not a torus. So that's not a desirable property. And so, you know, in my mind, so the main point of simplicial sets is to fix this property. Manuel, do you have any other reasons to like simplicial sets? I don't know. I think this is a good enough reason. Yeah. So so the simplicial category is just a category. The objects are the same. They're finite non-empty sets, but now we have all order preserving maps, so they don't need to be injective. Yeah, so you know, we have these extra basic maps. So just the map from p plus 1 to p, you know, let sigma I be the surjection that sends I and I plus 1 I. And so now these two basic maps generate all morphisms. Compositions of sigma i's with, you know, delta j's generate all morphisms. Yeah, so, and then, you know, a simplicial set is a functor from the, you know, from this simplicial category delta to sets. And yeah, so it's we have the face maps we had before, the DI maps, but now we have these maps SIs, which are called degeneracies. Oh yeah, so how do we get simplicial sets? Well, one thing you can do is if you have a semi-simplicial set, you can just sort of freely add degeneracies. So you just, so x hat is going to be, so if x bullet is a simplicial set, x bullet hat will be the, x bullet is a semi-simplicial set, this thing is a simplicial set, and the value on p is just going to be the set of surjections from p to q, or disjoint union over the set of surjections of xq. So I don't know if how many, you know, if how many of you like left con extensions, but you know, this is a left con extension. Yeah, so you know, if you have a semi-simplicial set, you can just sort of add in degeneracies. So if you take x0 to be a single point and the higher xi's to be empty, then this the sort of simplicial setification of this semi-simplicial set will have a point in all degrees. Yeah, so I don't know, like several of you, you know, sort of know about like sheafification. You know, there you take a pre-sheaf and then there's some construction that sort of freely just makes it into a sheaf that, you know, this is, you know, this is sort of analogous. It's like the simplicial setification of a semi-simplicial set. That's also a left con extension. Yeah, so the downside of these is, I guess, assuming any of your sets are non-empty, they'll all be non-empty. You know, so if you're thinking, hey, I want to model like a 4-dimensional simplicial complex, if you want to do it with a simplicial set, you're going to need, you know, sort of an infinite amount of information, or you're going to need at least, you're going to need like the xi's will be non-zero in all degrees. Okay, so semi-simplicial sets have only sort of one geometric realization. Simplicial sets have two. So one of them is it was called the thin geometric realization. You mod out by use this formula. So in addition, if you have a simplex, you glue it onto its faces, but then you also sort of attach it. You attach it downward to its faces. You also sort of attach it upward to the image of its under the degeneracy maps. Yeah. So these, just like you can include a p simplex into a p plus 1 simplex as its face. There are these collapse maps where you collapse a p simplex onto a p minus 1 simplex. Yeah, so what you should sort of think of is that the images of the degeneracies are not, I don't know, they're somehow, I guess the name degenerate is like, the idea is like sort of the image of the degeneracies are things that you don't really want in your space. So we're modding out by that. Yeah, and then there's a thick geometric realization, which basically, one way of describing it is just, a few ways of describing it. One is just use the formula that you used before, so just only identify things with their, only identify like a simplex with its boundary. Another way is saying just take your semi-simplicial set, use the forgetful functor, forget it down to start it with your simplicial set, use the forgetful functor, forget it down to a semi-simplicial set, and then realize it as a semi-simplicial set. Yeah. So okay. So here's sort of some comparisons. So one thing, if you start out with a semi-simplicial set, you could and geometrically realize it, that will be the same as you take your semi-simplicial set, turn it into a simplicial set, so you add in these extra degeneracies, but then you take the thin realization, which ends up collapsing these degeneracies. And if you have a simplicial set, there's always a map from the thick realization to the thin realization, because this is defined as just impose more equivalence relations, and this will be a homotopy equivalence. So for simplicial sets, up to homotopy, it doesn't matter which one you consider. Anything I should repeat, or any other questions? Okay. Is this mostly new? Like Ralph didn't talk about a lot of this?
For me, at least, yes. This is pretty much new.
Okay. Yeah. Yeah. Sorry, I should have been like clearer on the survey. I'm like, oh yeah, this is what I mean by. Yeah. Okay. So let's just sort of think like concretely, what are these two different realizations? So let's let xp be a point in all degrees. Yeah, so like in particular, if you took the semi-simplicial set, which is a point, if you start out with a simplicial complex, which was just a point, then you turn it into a semi-simplicial set, that will be a point in degree 0, and the empty set in all higher degrees, and then you turn it into a simplicial set, that will be a single point in all degrees. So let's ask, like, what's the thick realization? Well, we have a point in all degrees, so we're gonna, so I guess what you do is you start out with a point in degree 0, then you sort of take a circle, then you attach a triangle onto the circle like this, etc. Maybe this isn't clear. So what is this picture? Maybe one way of saying it is this space here comes with a natural filtration by like the less than or equal to p part. So I'm sort of drawing the stages of the filtration. So what I'm saying is, like, in the beginning, in the beginning, you start out just with like x0 cross D0, I'm not going to write delta. So cross D0, so this is a point, cross a point, so we just get a point. And then what you do is you glue on x1 cross D1. Well, x1 is a point, and this is a interval. And when you glue that along, when you do that attachment, you get this circle. And now then we glue on x2, which is a point, D2, which is a triangle now. And then how is the triangle attached? Well, the triangle has 3 sides, and all 3 of the sides, how are they attached? Well, they're attached along the maps from x2 to x1, but x2 is a point and x1 is a point. So all of the, all of the maps like D0, D1, D2 from x2 to x1 are the same. So what ends up happening at stage 2 is we just have a triangle where the sides are identified like this, etc. So I claim that this is going to be contractible. So what's the fundamental group? The fundamental group, well, so we can already compute the fundamental group because the higher cells, once you have the 0 cells, 1 cells, and 2 cells, the higher cells won't change the fundamental group. So pi 1 is going to be, well, let's name this edge A. What's the relation? Well, okay, so it's just A. So you go around this way, it's like A times A times A inverse. Well, okay, this is the trivial group because this relation is just A. Okay, so we want to show this space is contractible. Well, its fundamental group eventually becomes trivial. I guess the fundamental group isn't trivial here, but it will be trivial eventually. How do we compute the homology? Well, we can compute the cellular homology. So we just get, that's a bunch of z's in all degrees. Because, it has one p cell for all p. What are the maps? What's the map from degree 0 or degree 1 to degree 0? If you want, you can think of like this as like z of x0, z of x1, z of x2, etc. This is cellular homology. And I guess the boundary map, the differential, is going to be sum of the di's. So or and any guesses at like what these maps between these z's are? Like what's the cellular differential from?
Well, there's just one map every time, right?
There's one map. Oh yeah, I guess there should be.
There's like one. There's just like one choice.
Yeah, there's a typo. I meant to say d is the sum of like -1 to the I, di. So all you're saying all these di's are the same, and then it's just going to be a parity thing. So here, the boundary of this one cell is going to be the 0 cell minus the 0 cell. So that map will be 0. Like this map will be 0, but this map will be the, I killed everything, the identity. Okay, this map is going to be the 0 map.
Yeah, exactly.
But this map is going to be the identity map because it's going to send 3 copies to 1 copy.
All right, because okay, yeah.
So if you compute the homology, it's alternating between 0 and identity, and then the homology is going to be 0, and the fundamental group is trivial. So this whatever crazy thing it is, by Whitehead is going to be contractible because it is trivial homology and fundamental group. Yeah. On the other hand, like the thin geometric realization is just a point. Because, you know, in positive degrees, everything is in the image of the degeneracy so it gets collapsed down. So usually, you know, yeah. Okay. So, you know, if you have a simplicial set, usually the thin realization is it's at least a smaller thing. Yeah, it was obvious that a point is contractible. It was less obvious that this crazy thing was contractible. Are there any questions? Okay. Yeah. And then things oh yeah, so if you the whole a point was that they behave better with products. So yeah, so if you have simplicial sets, then you can endow their product with a natural simplicial set structure, and then the geometric realization of the product is going to be homeomorphic to the product of the geometric realizations. Yeah, so if we take Y to be this semi-simplicial set that has two vertices and one edge, and the higher ones are empty, and then you let X0 be the... Okay, so Y is a semi-simplicial set, X is the simplicial setification of Y. Then the product is going to be a square, which is what you want. Like the product of an, you know, Y is an interval. If you take the product of Y with itself, the realization, I don't know what it's going to be, but it's definitely not going to be a square because it won't have any two cells. But if you take X, which is this, you know, infinite thing, and then take the product and then take the thin realization, you're going to get a square. And so, you know, one can look at this formula. I don't know that I can make this formula make sense, but the idea is that when you you know, where does the magic happen? Well, you know, if you just took Y, you know, you take Y, then you build X, the simplicial setification. The realization of the thin realization of X will be the same as the realization of Y because you add these degenerate simplices and then you collapse them. But the idea is if you take the product of two degenerate simplices, they might not be degenerate. So they're, you know, degenerate means in the image of one of these SI maps. So yeah, so sort of having the degenerate simplices lets you make causes the product to end up working out. You know, because you think like, oh, I don't need these degenerate simplices, I'm just going to collapse them. But the product of degenerate simplices can be non-degenerate, and that's what allows, you know, even though like X morally is one-dimensional, it has this information in degree 2, and that's what allows the product to have non-trivial or, you know, non-degenerate two simplices. Okay, so that's simplicial sets. You can define simplicial sets and simplicial spaces exactly the same way, except now we take functors from simplicial sets, or, you know, from the simplicial category or like the injective subcategory to top instead of to sets. So now you're thinking like we're gonna instead of like having a set of three simplices, we have a space of three simplices. Great, whatever that means. We can define geometric realization using the exact same formulas. There's a technical thing that is annoying. It's no longer true that the thick realization mapping to the thin realization is a homotopy equivalence. It will be in good conditions, but there are pathological examples. You know, like if your set of one simplices is the topologist sine curve, you might run into trouble. but you know, yeah, great. Okay, so what were we, why were we thinking about this in the first place? Well, so we wanted to understand this formula in terms of geometric realization. So, you know, this kind of looks like geometric realization. We have a disjoint union, and we have, you know, disjoint union of a set across a p-simplex for all p, modulo some relations. And so it's going to turn out that the first three are relations corresponding to the face maps, and then the last one is going to be the relation corresponding to degeneracies. Okay, so yeah, and then why did we care? Well, because if G is a discrete group, then this is a model of KG1. Okay, yeah, so now I'm going to tell you a general construction that when we plug in specific example, or that will specialize to give the simplicial set, giving this. Okay, this is kind of a big thing. So this is, right, big as in intimidating formula. So this is called the two-sided bar construction. Yeah, so you know, let R be a space, or you can think a set with a right G action, and L a space or a set with a left G action, and here G is a group. You know, if you're scared of simplicial spaces, just think everything's discrete and replace the word space with set. It's still an interesting construction. So we're going to build a simplicial object. And to tell you what a simplicial object is, all I need to do is tell you, you know, I need to tell you p different sets in the simplicial set case, or p different spaces, or sorry, not p different. For each p, I need to give you a space, and I need to tell you maps between them. So given a group and something that the group acts on the left and something that the group acts on the right, it's also possible I flipped right and left. Maybe it's correct. It's correct. Yeah, so the set of p simplices are going to be R cross G cross L. And the face maps, you know, so what do we have? We have R, an element of R, G1, G2, ... GP, and then L, an element of L. And given this data, you know, the face maps go from P to P minus 1. So we have this list, and we want a list that's shorter. How can we make this list shorter? Well, you know, R has a G action, so one thing we can do is we can multiply R and G1. So that's what D0 does. It multiplies R and G1. Well, G is a group, so we can multiply G1 and G2. That's what D1 does. We can multiply G2 and G3. That's what D2 does, etc. So the zeroth map multiplies the R with an element of the group. The middle maps multiply elements of the group with each other, and then the last map multiplies GP or L by GP. And then because we have a group, you know, groups have units, so we need a map that makes the list longer. What do? We just add a 1 in the ith spot. Yeah, so this gives you, you know, a simplicial set or simplicial space if you know, if your things have topology. Any questions? Okay, great. Yeah, so so we're going to let star be the 1-point set with a trivial G action. So the claim is that if you apply this construction, I guess maybe the first thing you should look at is this part. Okay, so what is this saying? If you take B star G. Oh, I guess I should have written bullets here, whatever. Yeah, so if you take the, if you plug in G as your group and the trivial, the trivial G set, so just a set, a set with 1 point, and set with 1 point is only has one G action. I guess it's a right G action and a left G action, which is great. So if you plug this in, you get a thing that's configurations of points in the interval modulo the boundary. So that this boundary is a set of size 2, and that corresponds to the 2 stars. And then my claim is if you just mod out by G0, you get star on the left, but G on the right. A group is naturally a right and a left. A group is a set with a G action. And then I claim if you plug in G on both sides, you get G of the interval. Okay, so I feel like I should have had a picture for this. Do I have a picture for this? Who knows? I'll have to lose my beautiful circles. Okay. I don't have a picture for this. Yeah, so we should think of this. Any something. Is there like a blank slide? I should go find a blank slide. Whatever. Okay, I'll just write on this somewhere. Yeah, so let's think about this space. So what do we have? We have this line, that's the interval. We have a bunch of points on it labeled by like G1, G2, G3. And the points are green. So I claim that what does this correspond to? This corresponds to the element, well, star G1, like a semicolon G1, G2, G3, semicolon star. And then cross, well, we need an element of the simplex. And what's our element of the simplex? Our element of the simplex is exactly, so like the distance from here to there is going to be T1. The distance from here, G1 is going to be at the point, GI, write it in text, GI is at TI. Yeah, so this data is exactly captured by, our element of G and T1, T2, T3. And, what the boundary of the simplex corresponds to when like T1 equals T2 or T2 equals T3, but that's exactly a collision. So, when T1 equals T2, that's when G1 collides with G2, but that's exactly the boundary of the simplex, and sort of the, then we apply a face map and replace it with G1 times G2. And then with the other part of the boundary of the simplex, that's when, like, this point, like when T1 is 0, that's like this point marches over here, but in those regions, points vanish. And, points vanish if they go here or here. And points vanishing is the same thing. Well, G1, letting G1 act on star forgets the information of G1 because star is just a point. Yeah, any questions on like this identification here? Or like things I should repeat, or just like anyone want to say they're confused without any more concrete? Okay. Yeah, and then
G's in a group.
sorry.
Oh, sorry. Oh yeah, I was just wondering if G's like a topological group, is this like still true? Like, do you preserve like the topology
Yeah,
of G, I guess?
yeah. That the topology on here is exactly the topology there. Yeah, so this is true as for topological groups. Yeah, and so the next point is let's sort of think about let's sort of think about this space here. In this space, points don't collide when they hit 1. I guess this is 0 and this is 1. Points, oops, grabbed the wrong thing. So in this space, points don't collide when they hit 1. And so you should think of this space as like there's permanently a particle here. But I mean, that particle could be the identity. Oh yeah, I should say that the face maps or the degeneracy maps correspond to points labeled by 1 vanish. So in this space, points can be 1. In this space, points there has to be 1 point at 1, but saying there has to be a point at 1 really isn't a condition because you can think of that point as being labeled by the unit of the group. Yeah, and then in this upper space here, points don't collide or points don't vanish if they enter 0 as well. Okay, any questions? Yeah, so this space is equivalent to configurations of points in the interval. Well, you can collapse an interval down to a point, so you get that this space is equivalent to just G. This space, which I'm going to call EG, is contractible because you can smash an interval down to 0, but we're modding out by 0. So this one is contractible. And then this one is the model for Eilenberg-MacLane spaces. Yeah, these spaces BG and EG are important even for like not discrete groups when they, for G not discrete, this thing won't model Eilenberg-MacLane spaces, but it's still an important space and it is useful for like classifying bundles. Okay, and then the comment here is if you do the thick realization, all you do is you omit the relation that points labeled by 1 vanish. Yeah, so you should just think of it as configuration space, but now we got some points labeled by the unit, and those points can sort of pass through everything freely. And yeah. Okay. Oh yeah, so one thing to say is that if A is a topological group, so is BA. Remember BA or BG is by definition B realization of B star G star. Which is the same thing as just configurations of points in the interval. Mod I, or mod the boundary. Oh yeah, so I'm saying, if A is a group, well then configurations of points in the interval labeled by A as a group. Sorry, if A is an abelian group, then this is a group. Yeah, this is sort of maybe a subtle point, but if you have okay, so we have you have a point labeled by A, you have a point labeled by B. And okay, well, if they happen to be at the same location, and you have an abelian group, then you would just add them and get A plus B. But so this works for abelian groups, but this operation isn't continuous. You might when the group is non-abelian, because really requires a picture. Okay, so let's say you moved this point over to the right, and you were to add them. This plus this equals that. But now, let's say we're going to add the same thing, but now A is over here, B is over here. We're going to get B, and then right next to it, we're going to get A. Yeah, so I was saying, why is this not continuous? Well, this should be it's not continuous if A is not commutative, because like this point is very close to the point where A is just to the left, or of B, which would add to this point. So if you look at a path where the point labeled by A moves starting from the left of the point labeled by B and then ending up on the right, it's going to force that when they coincide, that this point is both, the left limit will be A times B and the right limit will be B times A. So they better agree, otherwise this addition isn't commutative. I should have prepped a picture for this. Sorry. Does this make sense? Yeah, so I'm claiming that when A is an abelian group, configurations of points in a space with labels in A is an abelian group, but if A is not abelian, then you could try to write down a formula, but it won't be continuous. Yeah, so the BA is an abelian group, so we can, it's a topological abelian group. We can apply the B functor to any topological abelian group, so we can iterate it. So yeah, so I'm saying if you iterate it n times, you just get configurations of points in the interval mod boundary. I'm going to delete this. So yeah, so what I'm saying, and maybe in words, is I'm saying like A, you can take A of, okay, so like A of I mod A of the boundary of I is a group. So then you can parenthesize that and take that applied to I mod parenthesized A of I mod boundary A of boundary of I of boundary of I. And then I'm saying this is the same thing as A of I squared mod A of boundary of I squared. That's what this equality is saying when n is 2. Yeah, so we should think about, configurations of points. So when n is 2, this is configurations of points in the interval labeled by configurations of points in an interval. So if you rotate one of the intervals, then you get configurations of points in a square. Yeah, so in particular, if A is a discrete abelian group, then if you apply this B construction n times, you get a model for n-fold Eilenberg-MacLane spaces. So, in particular, so KAN isn't a realization of a simplicial set, but it's a realization of a simplicial repeated n times set. Yeah. Any questions? Okay, great. Yeah. So then the next comment is that what does this B functor do? Well, on homotopy groups, B shifts homotopy groups by 1. So if you look at the long execs, we get a fibration coming from so I guess like G of I mod G of 0. This maps to G of I mod G of boundary of I, because 0 is contained in boundary. Like is a fibration with fiber G of 0. So we get a long exact sequence of homotopy groups. I guess G of 0 is just exactly same thing as just G. So we get a long exact sequence of homotopy groups. G of I mod 1 endpoint, and this is contractible, maps to this space. This is this is the thing we're calling BG. And then that maps to, the connecting homomorphism maps to I minus first homotopy group of G, maps to homotopy groups of G of I mod part of the boundary. So this is contractible. So we get, this is 0, that's 0. So this map is an iso. Yeah, so I guess when G is discrete, this just says that BG is an Eilenberg-MacLane space. But if G has topology, then this says that BG has the same homotopy groups as G, but they're just shifted. That recovers the statement here. Any questions? Okay, yeah. So here's some examples of before. So BS1. B shifts homotopy groups, so that's S1 is a KZ1, so B of it will be a KZ2. And we know another model for KZ2 is CP infinity, and we're going to prove uniqueness of Eilenberg-MacLane spaces. So this tells us that BS1 is homotopy equivalent to CP infinity. Both of them are Eilenberg-MacLane spaces for Z in degree 2. Another comment is that this the loops functor shifts homotopy groups one way. This B functor shifts homotopy groups the other way. So if you apply loops BG, you get that's this space of the same homotopy groups as G. And then another comment. So loops in B are one of them is a one-sided inverse of the other, but they're not two-sided inverses. Because one shifts homotopy groups up and the other shifts homotopy groups down. So if you shift up and then down, you don't lose information. But if you shift down and then up, you do lose information because you sort of send things to negative degrees, and then send it back up. But there aren't negative homotopy groups, so you end up losing that information. So the point is, if you apply, B loops G, pi 0 of this is going to be 0, but pi 0 of G is going to be G. Now you might say, okay, what do you mean B loops G? Loops G isn't a... I guess loops G actually is a group. But okay, yeah, the loops G is a group. But if you just plugged in a space X here, we could still make sense of B actually makes sense for monoids, and we can use more loops to make sense of the statement. So yeah, so looping in B one way. So loops up to homotopy is an inverse of B on one side, but not on the other. Okay, yeah, that's all I wanted to say today. I'm gonna stop the